Hello everyone, welcome to the class of ECE 593 Fundamentals of Pre-Silicon Verification. My name is Sandeep Jain and I am the instructor for the course. Um, we had a Zoom recording issue in lecture 1, so I am re-recording this session and making it available for students to view it offline. A little bit about myself. I am Sandeep Jain. I am a adjunct faculty at Portland State University. I've recently joined as an instructor and I work full time for Intel Corporation. I've been in the industry, semiconductor industry, for 28 years, and I'm currently a principal engineer at Intel. So during these years, I've done a lot of chips, doing various design verification of the chips, and I'm happy to share those experiences in the class with the students. Um, so a little bit background on the class today, ECE 593. It is one of the core classes, and one of the prerequisites is ECE 571, System Verilog. We do require knowledge about System Verilog in this class, and that will be required as we do the projects and assignments in the class. Assumption will be we don't have to spend too much time learning System Verilog, but learn about verification as such. There are some electives also listed here for students who are interested in making design verification as your career. So these electives will be helpful. And if you have any questions about these courses, please feel free to contact me. We can have the discussion. Some of the administrative details. Here is my name, contact. Here is my cell phone number. This is in case you need to reach for some urgent issues. You can reach me on the cell phone, but I prefer most of the students to use the emails. I check my PDX emails over the weekend, so I try to collect all the emails and respond to them over the weekend. Um, but time to time, sometimes students will need to reach me for any urgent issues. Then you can use my private emails as well, which I have shared with the class offline as well. And you could reach my cell phone for really urgent issues. Required books for the class. There are two books listed: Comprehensive Functional Verification by Wiley, Gross, and Reusner, and the UVM Primer. We'll be following these books closely, so I will highly recommend you to refer to these books. And there'll be course reading assignments and projects and such, which will be referencing these books. In addition to that, there are additional references, like one of them is Mentor Graphics Manuals. Now it's Siemens. So they do provide Questa and System Verilog manuals. You can refer those. And there's another book, System Verilog and Verification by Spear and Tumbush. This book is also nice to refer to. Prerequisite, ECE 571, as I talked earlier. Classes will be held Tuesday, Thursday, 5 to 6:50 p.m. in WCC building. I like to have students in the class to make it interactive class. Um, the class will be streamed on the Zoom. Students can attend on the Zoom, but it is required you to be present all the time. I'll be doing random checks for students' presence, and the class attendance will be graded. So please make sure you are attending the class in person, whether on Zoom or in the class, um, or on the campus. I prefer students to be on the campus, um, and students who are attending on the campus, they are required to be here on time. Any late attendance in Zoom or in the class will may result in unexcused absence. Then Canvas, there is a Canvas maintained for the class, and um, please check Canvas often. I'll be posting a fairly useful material. And then finally, some of the material used in the class could be copyrighted. It's mainly for educational purpose, and no, it should not be used for any commercial use by students. Um, So please be careful on the fair use policies about the notes. It is the grading for the course. This course is heavily focused on project. As you will see, um, there is a midterm exam, 10%, final exam, 20%. So exams are about 30% of the grade. 5%, as I mentioned, is for attendance, and all the remaining is for the project. So as part of the project, you'll be required to submit a academic paper, which will be 15% of your grade. There'll be final submission and in-class presentation, 20%, and there'll be a project weekly homeworks assignments, which will be mainly project-based, but it could mix some additional materials we'll be covering in the class. Um, and Most of the work, as I mentioned, like 55, 60, 70% of your grades is project only. So please make sure you are actively working on the project throughout the semester. It's a major portion of your grade, and this project is team based, and you'll get to work as a team, and there'll be some individual grades which will distinguish individual grades for the class. Let's talk about the project. So the projects wise, you're supposed to come up with a complex system to verify. One of the proposed project is you can use ALU based design and test bench, which we'll be covering in the class. I'm okay for you to use this and enhance the functionality. Here is one example of that, like where you can have multiple CPUs with caches in them connected over share bus to memory and memory controller. So I will prefer everyone to follow the same project. It's okay to follow the same project. Reason being, I want to encourage a lot of learnings from each other in the class, and emphasis is on the skills of verification and coding, and we can best learn from each other as well as in the class. So I'm fine if everyone chooses to have the same project, um, and uh, and alternatively you can create your own project, like which could be microprocessor based, cache based verification, PCIe systems, and so on. And You can borrow as much design as possible from the previous classes, but you cannot use licensed or commercial design because of the IP concerns. There is a big emphasis on plagiarism. Plagiarism won't be accepted. It will have serious consequences in the grading. Um, Even if you reuse your code, you have to give the credit where you got your previous code from, and or if you're coding from scratch, you have to mention that. So if I come to know about that design is being borrowed from some other sources, whether it's on internet or previous classes, and not um, declared, there'll be serious consequences for your grades. So, so please be respectful for others' code. And one of the ways one may ask is like how to avoid plagiarism when they are reusing the code, is to in your in as you write your code, like you can always put annotations and comments listing the sources which you have used for this code. And for example, let's say you borrow a verification IP um, of a checker from somewhere. So right where the code has been borrowed, above that you can create some comments that hey, this code has been borrowed from, and you have to list the source where you got it from, internet, or give the HTML address and so on. Right. And for project ideas, you are welcome to propose your project ideas. And this is a rough outline for how we'll be producing. Week one, you will start with setting up the simulation environment with a tiny ALU example. Week two, you're expected to form your teams and submit your project ideas. Week three, onwards, you will be start submitting weekly progress on your project as part of your assignment. And Week 9 of the class, you'll be submitting the final project. And Week 10 will be, you will have in-class presentation and academic paper. And then next week, following week will be the finals week. So this is a rough outline. I may change as the semester progresses based on the inputs from students, but this is more or less will be following this. Uh, Weekly assignments are due on Friday nights. I may provide some extension, um, but there will be penalty for this, um, and we'll go from there. Uh, so I talked about the project is team based. In a real world, when you work in a semiconductors company, whether it's a FPGA based company um, or a VLSI design as silicon based design ASIC company, more or less you will be working as a verification engineer. You will be working in a larger team, which consists of design verification and various other roles. To give that flavor or to give that experience to the class, I want teams to work, every student to work in a team. So in the class, like we'll have 4 to 5 teams. Each team should have 4 to 5 members. It's a relatively large team, but we want you to work as a team. And within the team, I want you to define certain roles. There'll be verification engineer role, design engineering role, and there'll be verification program manager role. So verification engineers, what do they do? Like they'll be responsible for coding the test bench components. They will write and maintain the verification plan for your project throughout the duration. They'll be helping on developing tests, verifying the design. So 60% of your team should be verification engineers, right? Like for example, if you have a 5 people team, 3 engineers will be verification engineers, and remaining will be design engineers. So 40% of team will be design engineers. Uh, so design engineers, what do they do? Like they will be responsible for coding the design and the test or design and the verification. They'll be helping on components coding as well. And once if they're done with their task, they can occasionally help verification engineers on some of the verification tasks as well. They will be responsible for writing and maintaining the design requirements. So design requirements for your project should be clear and should be in the sense where it's a verification ready requirements. Um, and For example, like there are some temporal protocols used in the design, for example, a request happens and 2 clocks later grant happens. Um, so such requirements should be listed explicitly, um, and along with general design requirements. Designers will also help with the debug, or and they'll be responsible for fixing any design issues found. They will also do the integration of all the design unders test bench, and design. And 40% of the team should be designers. Finally, there is a special role defined, program manager role. This is every week, one person in the team should rotate into this role. So this person will be, look, for example, you have 4 people team, week one, person one can be the verification program manager, week two, second person, week three, third person, and so on, right? And then after 4 weeks, you rotate again, like, first person again takes it, second person again takes it. So one person rotates into the PM role every week, and they'll be responsible for chairing a 30 minutes meeting at minimum with all the team members present, and and we'll be conducting the status report or final submission and so on. um, they can have more working meetings, but one is minimum required to meet as a team and do it. Um, and Once the plan, I usually recommend 2 meetings, like one at the beginning of the week and one towards the end. The first one becomes your planning meeting, where you plan out your week, what verification program manager wants all the team members to do. And the second meeting is more of collecting the status and closing before submitting the report. So usually I prefer 2 meetings, but one is a minimum required. Um, and This verification program manager will be responsible for submitting the assignment for the week. This will include your status report, design specs, verification plans, all your code, results, and so on. And finally, this person is supposed to work um, cohesively with all the team members and make sure that team goals are met. So overall, if you look at the team structure and the project, I'm trying to mimic the environment you will see in a real workplace when you become a VLSI verification engineer, where you work with larger teams and everyone gets assigned some tasks, and you on a weekly basis you track the progress for your project till you have finished it. So we are trying to do something similar, like so that you can gain that experience not only for verification coding and all, but also team communication, that you how to work with your team members. Um, I talked about every week there'll be a status report due. So verification engineers should get used to documenting their work. It's important that you every week or every assignment you create some sort of report file which accompanies your assignment. And this again is mimicking the real world scenario where every week, as verification engineer, you're supposed to submit status reports of your progress, right? So it's 1 to 2 page should be submitted. It should at least include these items, like objectives for the week, what did team plan to do, what were the status for the week, and what were the issues found and resolved during the week, what were the action plans for resolution if some issues are still open. um, it should also include some of the roles of what each person did during the week. um, you know I don't need like very big write-ups on what every team member did, but there should be some indication of what each team member do. It's a teamwork, so every week I expect every team member to contribute, so that we can grade individually also within the team as well. Most of the grades will be team grade for the assignments, but um, like I could um, take off points for individual roles based on the roles and contribution for the week as well. Um, and along with that, like the VPM will submit any changes to the validation plan. If you are doing it for the first time, you'll be submitting the whole plan. Otherwise, like you'll be maintaining the changes and highlight those changes as part of your report. Similarly, same thing for the design spec and requirements. You'll be tracking your design specs and submitting those and highlighting what changed week to week. And uh, submit the source code for your test bench, um, and provide the cheat sheets. Like in case I want to reproduce your results, there should be very clear cheat sheets on how to obtain those results. We'll also include the coverage report, and will you will also submit any bugs found, how you found them, how you debug them, what are your action plans. Hopefully, you'll resolve those within the week. But if you can't resolve them or want to push it out to next week, do indicate like what's the resolution plan for that particular issue. With that, like there is a homework assignment one due. Like it includes the first assignment. More details will be posted on the canvas, but at a high level, you are expected to set up the Linux environment, and you'll be running a simulation on Tiny ALU. And as part of the submission, you will be submitting your cheat sheet, code, simulation waveforms, coverage report, as such, right? Um, A little bit more on the administrative details. You have to follow the professionalism and academic honesty. Be a good team player, as a lot of grade is dependent on your grade project. So be a good team player. Um, work to work and learn in harassment-free environment. Um, Exhibit highest professional standards. Plagiarism is not allowed. So if a person is caught with plagiarism, there could be serious consequences, and any misconduct will be immediately reported. Um, Regarding the exam instructions, exams are designed to simulate a interview format, and when a question is being asked to elaborate something, use your own words. Do not cut and paste answers from existing sources. Here is an example. Like for example, question comes about what is DPI? It's a direct programming interface, and you provide more information on it, technical information on it. But what will be unacceptable is if you just copy paste directly from a website, right? Like in this, if you compare, uh, the code is pretty much the same. Like um, basically, it is found from the book, so it's pretty much unacceptable, and uh, it will not be accepted. Secondly, notes will be a lot of people use notes, uh, you know, uh, but you cannot use notes of others. You have to use your own notes. That won't be allowed. Finally, like midterm, this is a rough outline for chapters which will be covered as part of the midterm. Chapter one, so comprehensive functional verification book. There are 4 chapters which will be covered as part of the midterm, and in the UVM primer there'll be 10 chapters. In addition to that, there'll be some additional materials where we jump around in different sections. We may apart from these chapters, there could be some additional references for, like for example, for coverage in chapter 6 and 7. So those, as long as we cover those in the class, that will be all due for the midterm. So that's all on the administration. So let's jump into motivation for verification, right? So next few slides will start to look at verification as a role in a semiconductor company, and why you should feel excited to become a verification engineer in your career. Looking at semiconductor industry, right? Like semiconductor industry is big, it's huge, right? Like in 2022, the revenues were exceeding $600 billion. Like that's a very big number, and year to year there has been annual growth of big dollar numbers, right? So semiconductor industry has been around since the first transistor was formed. Moore's law came in place where every two two and a half years, the capacity of silicon doubles. All right, and because of that, like there has been tremendous applications being found around the semiconductors, and there are several big semiconductor companies in the space sharing this revenue. Overall, like the growth is big, and to make these revenues possible, they have a big need for VLSI engineers and verification engineers. So this trend of growth is expected to continue for a very long time in the future. So there's a lot of money, high volume, high complexity, and that's why they need very talented engineers to make this industry possible. Right. There are a huge number of applications coming up. Everywhere you look around, there is silicon being used. Your cell phones, your sensors in the cars, your automated systems in the home. Everywhere there is silicon, and to make those silicons, you need engineers, right? So, how do we, so this slide talks about a very high level view of what happens that um, in a development cycle of a silicon, right? Like so we are making a silicon or application specific integrated circuit, um, and there are various stages that a particular chip or product goes through before it goes into production, right? So the whole work is divided into two functions: pre-silicon and post-silicon. So please, pre-silicon functions, let's start with post-silicon functions first, and then see like what do we need to do before these things happen for post-silicon. So post-silicon wise, your end goal is to ship ASICs or packaged parts to the customers, right? um, and before that, like, and all of that happens on a silicon. So you start with a silicon grain, silicon grain you find, and you pull it in a ingot and you form like a silicon ingot, right? Some company sells that ingot to and then you take that ingot, you slice it into blank wafers, and then on wafers, then you will be doing some manufacturing processing steps to 20 to 40 steps, and then you get a final processed patterned wafer. These wafers, they each of this pattern is basically one chip, which is being imprinted onto the silicon. Then you cut these parts out. Then you are going to take this wafers through various stages of verification, post silicon validation cycle. You take the wafer, do the wafer level testing, then you slice the parts out of it, slice and dice, and then you'll be testing these individual dies, and then all the good dies out of those, like, you'll throw some bad dies out, and then remaining dies you package them into packaged parts. And then once part has been packaged, you again do the testing, and then that you'll discard all the bad parts and send out the good parts to the customer. So as you can see that, like, during this whole process, validation plays a big role. That, at every step you have to do some sort of validation, because that validation allows you to take, weed out bad parts, and keep the good ones to the customer. And another thing which happens is, like, we want to find those problems which could exist in a final silicon, uh, as soon as you can, right? So what can happen before, before catching these issues in post silicon? um, there's a lot of pre-silicon work which happens to make this silicon possible, right? So let's look at now pre-silicon as a function. So in pre-silicon, there are various roles defined. Like, so now there is a planning phase, there's a front end phase, and there is a back end phase. Let's look at these phases within the pre-silicon domain. So planning phase, here you get the um, requirements to make a product. Let's say you're making a cell phone. In a cell phone, you every generation of Apple iPhone or Samsung Galaxy, Samsung phones, you are getting new features being added. Like, for example, I have a better resolution camera, I have these touch sensors. So you take all these product requirements and translate them in terms of what needs to happen in hardware on a silicon or software. And that's what architects do, that they take those requirements and map those requirements into the silicon requirements. And they will be they plan out, how this whole development will happen, and how the features will be implemented into your silicon, right? So based on that high level architecture, then this microarchitecture is defined, where you break this uh, uh, whole product into smaller functions, which are called, we call it system on chip. You're making system on chip which has like a lot of functions, and you break them into smaller domains, and each of those domains will have a micro architecture attached. And that's where you write the requirements for those microarchitecture. And then design happens after that, like, where design will look at those requirements and translate those requirements into your RTL code. That RTL could be in system Verilog, or VHDL, or any other language, right? So based on this planning phase, the front end work starts, right? Like, where you are you have defined your requirements in terms of specifications, and then you take those specifications and you create some sort of you know state machines, diagrams, and then based on that, you will code your RTL. Then once you have coded it, you compile it, run simulations, do the verification, and then uh, you do it in iterative cycle, like, because there could be some changes needed, so you'll be always doing these things in iterative cycles. And once your design has been verified that, hey, everything looks good, then you give it to the backend team who will synthesize your RTL. They will do the place and route, like, that is how that design will fit onto a silicon, right? Like, you decide place and route for that. You do the timing verification. Once that has been done, then you again do the timing based verification on an actual pattern of gates, how they behave on a silicon. Using the timing information, you do timing verification. And if you find an issue again, like, you go back to previous stages, right? So this whole design verification happens in continuous loops. And once design has been fully verified and it's ready to tape out, the term we use is tape in. um, and it is sent to the manufacturing processes, right? Like, that's when this particular you know uh, fitted design will be etched onto your wafer, and will be processed through these steps to come be imprinted on your silicon, right? So all in all, there are several stages of making a final silicon. um, and what is most important, right? Like, what's the most important milestone in this, right? And the answer will be that, the decision about when do you tape in your design to your wafer manufacturing or processing. That is one of the most important decisions, um, because, like, once the design has been imprinted, what you'll find is the cost of making these wafers, or cost of manufacturing your silicon, is very high. And if some wrong design goes into that wafer, it can cost you a large amount of money to recover. So in all this process, like, this separation of pre-silicon and post-silicon, that's one of the very important milestone when that should happen before you go into your production. Another one is, like, when do you start shipping to your customers, right? Like, that could be perceived as, like, one of the very important milestone as well. That before you ship to the customer, you want to make sure everything, starting from initial planning to final packaged part testing validation, you want to make sure everything make uh, satisfy the needs of the customer, like, what features we promised, they're working correctly, and so on. So ship dates and tape out are one of the important milestones. Now, looking at verification, we want to make sure that verification is complete, right? Before you ship the part to the product, or to the customers, or when you decide to tape in your design for manufacturing, right? So this is a verification. Knowing that your verification is complete is important objective. Now, we talked about all these stages or phases of pre-silicon development or post-silicon validation. What is known is, like, it's much easier, if a bug can be found. Bug means like a problem in your RTL code. It can be found early in the development stages. It's always cheaper and faster. As you go into later stages, every later stage in um, time and space is more expensive to the product development cost if it is found later, right? Like, so you want to find all the bugs before you can fabricate a design, right? um, and so how do we do this is, like, this requires like a methodological approach. um, so the methodology is important, right? Like, whether your design is big or small, whether you are doing ASIC based design or FPGA design, you need a methodological approach to achieve your targets of verification. Let's consider a black box mux, right? Like, so you're given a challenge that you have a mux which has X, Y, and Z as inputs, and some result comes out. And then you're being told that, you know, there's another mux which behaves the same, X, Y, Z, and result. Um, how do how do you make sure that two of these designs behave exactly the same, right? Like, these are black boxes, you don't know what's going inside it. um, then you take a white box approach where you look inside the design. What you'll find is the mux 1 is implemented with and or gates, right? Mux 2 is implemented with NAND gates. So implementation is different, but behavior is supposed to be same, right? So how do you test that two are the same? Well, two of these designs are the same, right? First, you need to figure out, what needs to be tested, right? What you'll find is, what you will say that is, if I toggle X, Y, Z as inputs, I want to see what happens for the results. If input vectors on both of these designs match and the output vectors on both the design match, we can say that both designs are same, right? But in order to do that, like you have to simulate 8 times to permutate through all the three combinations to make sure both designs are the same, right? But like instead of then 8 vectors, can we reduce it by using some sort of random tests, right? Like, can we, if we run the random test, we have to iterate through all 8 of them to make sure all the possible combinations have been tested. Then only we can say that results are the same. But knowing the design, uh, you know can we bind the case? Like, do we have to really test everything, or can we uh, get away with minimum set of vectors, right? Like, so we can probably get with um, 5 vectors to verify this design. um, how about like we just look at min plus 1, max minus 1, and something in between, right? Like if we take that kind of approach of 5 vectors, what you'll find is that's sufficient to cover all of them. Like, because what we have done is we have covered at least all values of x from 0 and 1, y 0 and 1, and z 0 and 1. So we have covered all of those possible values that each vector can take, and then we have looked at the outputs, right? And then randomly we pick one of the in between where you're looking at the combinations of 2 or 3 vectors to be in that boat, of same or different as well, to verify that, hey, we have comprehensively covered all possible conditions, right? um, so now, if we take the approach of exhaustive testing, why that is a challenge, right? Like for a small mux of 3 inputs, it takes you 8 combinations to verify all possible states that that particular design can take. What about like bigger complex designs, right? Like if you look at a x86 CPU, just the instructions of simple x86 CPU, it has approximately more than 7,000 state bits to define states of x86. And to verify that, it will take you 2 raised to power 7,000 bits, which is equivalent to about 10 raised to power 2,000 vectors to make sure that all possible combinations of those state bits have been verified. How big that number is, just to give you a comparison, that it's estimated that total stars in our universe is 10 raised to power 24. And we are talking about a astronomically big number here. So number of vectors needed to just verify one simple x86 CPU is astronomically big state space. Why is that a concern? Because in order to verify this, let's estimate how long will it take to verify it. To break this problem, let's look at just you're verifying a multiplier which has you're taking two 32-bit value vectors and doing a multiplication in them. So there could be 2 raised to power 64 possible input sets, right? So that will require you 2 raised to power 64 combinations to um, verify all the possible conditions, and which is equivalent to about 10 raised to power. If you convert from binary to decimal, it will be about 10 raised to power 19 vectors, right? Which is smaller than universe. But let's figure out how long does it take to verify that. Let's say a simulator can run 2 raised to power 32 cases per second, right? Like when you say, oh, there are 2 raised to power 64, right? How long will that take? Um, what you'll find is like it will take you 100 years just to verify a 2 32-bit value multiplication. You know how we come up with this is this table, right? Like you can see that uh, uh, in 1 hour you can probably run about 2 to the power 12 vectors. In a day you can run about 2 to the power 16, and so on. If you keep doing it, you'll find is it will take you a century to verify a multiplication on a simulator running on a server today. So which is practically not possible, right? So exhaustive testing is not possible in today's complex designs, because we are talking about, like, billion gate designs. Like, in addition to this CPU states, there could be other buses, protocols, memories, graphics. There could be so many ASICs, or so many designs on your ASIC that um, exhaustive testing is not practical. So if we don't test, what happens? Like, these bugs escape into our hardware, right? Like, we, uh, all the companies, all the engineers, they try to do their best to find all possible bugs they can, because we, as we said, like, we can't test everything pre-silicon or post-silicon. So we need to figure out, you know, we need to um, we need to take the risk that there could be bugs hidden in your design, right? Like, which escape. And there was a study done in 2006 paper by Sarangi et al., where they looked at published data from several companies. Like, they looked at famous AMD K6 processor, Intel Pentium processor, Athlon, and so on. IBM has shipped. So, so they looked at historical data of they looked at data for what happened to those products when they were shipping. What they found is each of these products had um, design defects found after the manufacturing. Like, and the number of design defects found is pretty large, right? Like, if you look at K6 at 18 bugs, Intel processor at 92, Pentium 4 had 99, Itanium has 100, and so on, right? Like, so what we find is, like, a lot of these products are shipping with bugs in them in real silicon. Um, and these bugs escape our verification practices, and they make it their way into the design, into the real world. Um, let's look at some of them, like, some of these famous bugs. 94 Intel Pentium bug. It dates back quite a bit, but that particular bug, um, you know, I'm going to pause for a moment and come back. My battery is almost dying, so I want to make sure. Um, all right, let's continue. So, what do these bugs do? Like, how do they impact the companies? So, one of the most famous one I want to talk about is 1994. It's a little bit dated issue. They were Intel was shipping these Pentium 4 processor. They were like very big news for the industry. Pentium 4 was doing good, but then suddenly they found some rare digital errors. Like, so when you are doing computation, that there was a FDiv bug, which results into 1 in 360 billion cycles. There could be one failure. There was a fourth significant digit error, which happens um, very rarely, like, where very rare combination of input vectors was resulting into one failure in 360 billion cycles. So when you run it, then there was another other issues found in ninth and 10th digit, that 1 in 9 billion, it could create problems, right? Um, so basically, these bugs were very rare to find, but it created a big problem for the company, where company had to recall a lot of their shipping products. And Intel was a small company back then, and uh, even though it was a successful product, Intel had to take several $100 million loss, and it brought Intel to a verge of total collapse for the company, right? So point in the case, the key point here is that some of these bugs can be very um, uh, dangerous for the business, for the company, right? Like, because they can result into product recalls and various other kind of issues. So these bugs are huge liability for, if they escape the silicon, or if they escape the pre-silicon verification, they can create huge problems for the company, right? Other examples are, there were Pentium F001 issue. There was an invalid operand and compare exchange, which halted the processor and required a reboot. There was a fmul bug found, which round up the mode and certain mantissa values, and this also happened like very rarely. More recently, like if you look at newer bugs, every year or other year, you might be hearing about famous issues which catch a lot of media attention, right? Like more recently, there was a meltdown and Spectre security bugs vulnerability found in all the AMD, Intel, ARM, IBM, Qualcomm, all sort of processors. Hackers could get into the side channel attack modes and steal the secrets from your computer. Like, they could steal this credit card of users. So these kind of issues, they can result into massive liability for the companies. And some of these are not really key functionality of the, these are not really key functional bugs, but somebody exploited some vulnerability to find the secure information hidden in your chip, right? Um, then there was AMD had a faulty random number generator. Like you're talking about random numbers, they're supposed to be random, but still, if there is a bug in generation of these random numbers, it can create a lot of problems, right? So all these bugs, they get found in post silicon, and they escape the pre-silicon world, and we have to find ways where we can find these bugs as early as in our design. Moving on. So now our second vector is that our design complexity is increasing year by year, like as the Moore's law has been there for several decades. If you go back to Intel's 8080A processor, like the very first processor, it was just 4,500 gates on 6 micrometer process with 20 millimeter square die. Like the die was so big, 20 millimeter square, but it could fit only 4,500 transistors. And generation after generation, Intel kept improving these number of transistors which can fit into per square millimeter of the area. And because of that, they could grow their chip sizes, shrink the process node, and pack in more transistors on a silicon. And that trend has been there for several decades now, right? Like now we are talking about 4 billion, 5 billion, and 6 billion uh, uh, gate SoCs. More recently, there has been development about 3D stacking, chiplet based designs, which have kept this curve intact. Like so we for foreseeable future, we don't see any slowdown into how many transistors you can pack into a chip. And what that means is the complexity of verifying such large designs is growing tremendously as well, right? So, so if you look at the ninth generation Intel i9 shown in this diagram, it has 8 cores, 16 threads, 16 megabytes of cache, and it runs up to 5 gigahertz, and it has 6 to 7 billion transistors, right? It has a full system on a chip, right? Like which can um, perform very complex operations and high computation, right? When going from 9th generation to 10th generation, Intel is uh, there is a new process. They keep increasing the features because of the availability of silicon. They can now process uh, video encoding to be 2x faster, or graphics capabilities are becoming 2x faster. Wi-Fi is 6 is being introduced. New features are being added. Thunderbolt. So generation to generation, as the number of transistor increase, we can pack in more functionality into our SoC. And what that means for verification engineers is that it will increase challenges for verification engineers as well. Same trends are being observed for FPGAs as well. Intel recently introduced. It's a little bit old news, but they recently introduced a 43 billion transistor FPGA, which can pack in very big designs. So modern designs are complex. There are a lot of functionalities in it, and to make these chips, you need very large design teams, right? Like you need very large design teams and very big verification engineering. And then in order to ship this product, there's always a pressure to finish the design and verification quickly and tape out the chip. And as part of as the bigger and bigger designs are coming, there is a big emphasis on reuse. Like we cannot design this whole thing, such big mammoth, in the first go. Like you have to reuse a lot of existing design components available to you, or verification components available to you, and so that you can keep spinning the products faster. So all these vectors which are driving the modern designs, they are increasing the complexity, and that's something a verification engineers need to comprehend so that they can plan their verification strategies to meet the demand of these designs. So what we discussed so far is that there are these um, another thing which is being observed as part of the development cycle is that the designs change frequently, right? Like as the product goes through the development stages, in the middle of the design, in the middle of the product development, there could be request to introduce new features into your product, right? Like the marketing team is always responding to changing landscape with competition and customer demands. So marketing and architecture, they could keep coming up with new features, and they want to pack those new features in the next earliest product which is coming out to the market. What that means for designers is that there will be constantly new features being added, or the designs could be tweaked. That designer thinks that, hey, my previous design was not optimal, so I need to do some tweaks because of optimizations or because of bugs. So because of all these front end changes where the requirements are changing or designs are changing, it puts a lot of pressure on the backend teams that if anything changes up in the chain, will have ripple effect throughout the big chain we defined earlier, right? So so that's another vector we need to consider well while coming up with our verification strategy. um, and then this kind of late stage development, what it means for verification and bugs, like it creates new set of bugs which for a new functionality there could be bugs just for itself, but there could be dependence on previous design, and it can introduce new kind of interactions with the previous design being done, and it can introduce new bugs for the old design for which you had already um, finished verification. For example, if you look at this chart shows number of new feature requests. So this is a real request that through when the project is executing, that design, you start with some requirements which have been frozen, but suddenly in the middle there could be a big splur of new requests coming in, and then that dies off. Then new requests come in, then that dies off, and then just before the tape out, like they want to get these features last moment, right? Like they keep introducing new requests, right? And if you look at the bugs will follow similar trend, that like the bugs die off, that hey, your design is fairly stable, and then suddenly you will see like bugs start to creep up. Many and these new features and bugs, they can require weeks worth of simulation time just to finish the verification. Next observation we have is that the cost of manufacturing is high and time consuming. We talked about the silicon wafers, like this is a real wafer being held by someone. Like you can look at the size; it's almost like a big 16-inch pizza in your hand, which has thousands and millions of ASICs which can be packaged into individual parts. Um, so, what's the peculiarity about these manufacturing is that the cost of manufacturing is high, and it has been going up as well, generation over generation of the products. Um, and in the as you look into post-silicon world, like there is less visibility to identify where the problems are occurring. Like if something fails, how do you find out where the failure is, why the product part is failing? The visibility is less in finding where the issues are, and then once you can't see something, how do you resolve that issue? How do you find where the issue is, and how do you resolve it, right? um, And then once, like, let's say by some of the debug methodologies defined for post silicon, you are able to find bugs. How do you get it fixed? Like, because once the product is done or taped out, a lot of designers move on to do other work or other next generation of products. Then there can be extensive delays to get things fixed eventually, right? So all this post-silicon world of bugs and debugging is painfully slow, and if something has to be fixed, it's very time-consuming and costly for the whole product development costs, right? Um, so let's look at next observations. These are various observations we have been discussing in what happens in the real world. One is, um, if you look at the final design, like it can be implemented in a low level description language, like where you're describing uh, various gates into the gate format. But using of RTL abstraction languages is also very important. That you want to abstract the design into RTL languages, like, and then there is a continuous evolution of languages as well. VHDL, Verilog, System Verilog, C, System C. Um, there are a lot of coding languages being floating around, but the key point is, like, you need some sort of um, RTL language which makes easier to test and debug. Um, and so that establishes the need that you need a language like System Verilog for design and verification, so that a design can be easily debugged and methodologies can be defined to debug it better, and as well as, like, verify the design better, right? Um, Next observation we have is, like, that if a bug is caught early, it's better. Like, the cost of bug um, increases later stages you find. So we need some sort of methodologies which can allow us to find bugs early, right? And so you want to define methodologies so bugs can the design can be tested early, and then you can find bugs early in your design. Um, So now let's look at some of the data, industrial data. We looked at, there was an industry study done by Siemens or Mentor Graphics, where um, various kind of design projects were interviewed, right? Like, they collected data from ASIC and FPGA companies, people actually doing the work, and they have been publishing the trends in the industry on what has been happening, right? Um, so one of the trends is, especially for verification, is that for a product development, one question was asked is how much time is spent on verification. So, so, so there is a at average, people or teams spend more than 50% of their time just doing verification. If you remember the pre-silicon and post-silicon stages, like, there is so much of functions all across the board, but out of if when people are asked where is the time spent, um, more than 50% of times of engineers goes into verification, right? So if you look at the trend, like, uh, the peak is around 57%, or like more than 50%, and average is also above 50%, right? So um, and let's say, like, if your design is complex, and you need enough time to finish your verification, and if you want to tighten the schedules, it will increase risk in your project because you need a tremendous amount of time to do verification, right? Second thing is, like, the same trend is seen in the FPGAs also, right? And a lot of times, because of this reason, verification or validation becomes in critical path for a product development. By the way, I've been using the term interchangeably, verification or validation. Usually, um, any work which is done pre-silicon is referred as verification, and post-silicon work is referred as validation. This is just a convention, but no rules. But that's a more common terminology. The pre-silicon um, is called verification, and post-silicon is called validation. Now, when you look at the team sizes, right? Like at average, over the years, you saw that the design complexity is increasing. There has been effort to keep the headcount of engineers the same, but the reality is that average number of engineers has been going up. And one of the another trend you will observe is number of verification engineers per design has been increasing faster at a faster cadence, right? So design is increasing at certain growth rate. Verification is growing even faster. There is more need of verification engineers than design engineers. And this is how we have structured our project also, just as a note, that we have structured it to have 60% verification engineers and 40% designers, right? It follows a similar model as in the industry, right? Um, and then if you look at the mean peak number of engineers on a FPGA project, it follows very similar trend that verification engineers, number of verification engineers still less than designers, um, for obvious reasons. So one of the reasons FPGA still uses lesser number of engineers is because the risk or cost of fixing issues in FPGA is smaller than the ASIC, because in FPGA, if a bug is found after the product release, you can always issue a patch which will go and fix that issue in the design. It is still costly, but the comparative cost with respect to ASIC is much smaller. So FPGA projects are generally willing to take a little bit more risk than a ASIC project. ASIC projects are realizing that the cost of bug is so high, they want to catch everything early, so they are willing to allocate more resources early in the project. Whereas FPGAs, the trend is going to reverse sometime in future, but currently it's about same number of engineers, design engineers and verification engineers, right? So next trend is along the similar lines that when asked for where are the engineers, ASIC engineers spending time in design versus verification, even design engineers are starting to spend more time. That trend is like, they spend about 53% of their time doing design itself, and 47% of designers' time goes into verification. So, which is a very surprising fact that designers are also they become verification resources during the project, right? So there are pure verification engineers, and then designers also start to um, work towards verification. So if you look at the total count of verification, it's much higher in a pre-silicon world, and same trend can be seen for FPGAs also, right? Um, and by the way, remember that in the earlier in the project for your projects in the class, we talked similar structure where the designers allocated for the project, they will also help in verification functions also. So if I try to summarize what we discussed so far, right? So in pre-silicon world, um, we talked about the validation challenges like state explosion. The um, the amount of gates and states in a design is exploding, and so does state explosion. Like in order to verify everything, there's number of states is immensely large. Um, and since we cannot test everything in the pre-silicon world, we use targeted or other methodologies to test. And because of that, like verification can never be 100%, right? Like a verification engineer saying that, hey, I've done 100% verification of the design is always going to be false, because practically that's not possible. But you can test to a particular targets and verification plans and call that complete, right? But not entire design is not never tested fully, right? So because of that reason, verification is never complete at any given time. Even for the products which are shipping in the market, there could be some, as we saw, there are bugs hiding in every silicon which is shipping. So that's a known fact, and that's a verification challenge. Next challenge we talked about is design changes frequently, and because of that, you need verification environment which is adaptive enough to allow these kind of changes to happen. Right? We can't allow changes to happen all the time, but changes, that's the nature that changes will happen, and our verification methodologies have to be adaptable. to deal with the changes in the design. Then let's talk about DVV as a career, design verification engineering as a career, right? Um, we talked about like there is a huge market space for semiconductor industry, and there's always new exciting products coming, like for AI, for TPUs, for graphics, bit mining. There are always new exciting technologies being on the surface, and one thing common in all of them is they need silicon, and there is always exciting products which need talented engineers, and DVV is going to be a good career for foreseeable future, right? And why companies spend so much money in it? Because companies have brand loyalty, right? Apple, Intel, Coke, all these product companies want to ship high quality products to their customers, and verification is a key piece to find all the issues so the customers don't see them. Customers are happy when their products work flawlessly, right? And the cost of recalls is very high. Like there is this old data, 2011, $1 billion loss to the for the chipset recall. So we took some other examples of Pentiums and more recent recalls. Each of these recall costs companies a lot of money, right? So these are like costly areas, and companies are willing to spend money in the development cycle so that they can catch these issues early, right? So verification engineers, they provide independent um, views about verifying the design, right? So DVV engineering role is a good role. It brings good things to life, um, and the DVV engineers become expert of knowledge of architecture requirements as well over the career. Like because you're working with the front end teams to understand the architecture, microarchitecture, and design. So you gain a lot of expertise into architecture as well, right? Um, One of the approaches DVV engineers do is like they are always kind of pessimistic, that they always look for issues into a good scenario, right? But they maintain the positive outlook that at the end of the day we will tape out, uh, but they always assume the worst, that there will be some bug hiding into any statement anybody is making, right? And DVV, like even though we are working with a lot of abstract concepts, but um, it's a very systematic, methodology driven approach where DVV engineers get trained on, and then they can apply that and make uh, make the quality of products better and bring good things to life, right? We talked about verification and validation. So verification was pre-silicon was verification, and post-silicon was validation. Another differentiation is that verification engineers ask this question, that the design meet its requirements as specified by architects and designers, right? Um, so they're looking for ways to answer that question, right? Validation is looking more towards the customer. They said that, hey, what's the feature you have asked, and does my product and system is able to deliver that customer experience or customer requirement um, correctly, right? So remember that we talked in the phases that you start with the customer requirements and translate that into architecture or microarchitecture specs. So verification looks at the specs and verifies whatever the RTL code is to those specs. Validation looks at customers and says that, hey, what's my end customer requirements, and is my product meeting those requirements, right? So that's another way to differentiate in definitions of verification and validation, right? Um, let's talk about the design hierarchy, right? So one of the things we do in complex designs is divide and conquer, right? Um, so we want to take the whole design and break it into smaller blocks, right? Uh, what does that do is like it makes design more manageable. It will have and the one of the typical approaches is you break the whole SOC or design it by functions. One example is that we talked about some of the Intel processors. they will have bounded functions of, hey, graphics is done by GPU, computation is done by CPU, caches are storing the and there is a system agent. So basically, and there is a IO. So basically, based on the function, you can divide your design, right? And what does that allow you is that each function can be given to a different designer and verification team. So you can divide the engineering effort across multiple teams easily when you have bounded your um, design into functions, right? Secondly, it allows you to enable reuse, like, there's a term for IP reuse, whether it's a verification IP or design IP. Um, when you have broken it by function, once the function is developed, it could be reused over and over again. One example is that, hey, um, I have done a PCIe Gen 5 controller. Um, Once that is done, I don't, the specs are same. As long as I need to use PCIe Gen 5, I can just reuse it across multiple projects. Or you can buy that IP from a IP vendor company and use it as it is in your design, right? And this brings to the point, like, in if you look, you remember going back to the project we discussed for this class, we did say that, hey, IP reuse is okay, like you can reuse the IP, but you cannot just steal someone IPs. Like, you can't say that, hey, Siemens has developed this IP and I'm going to just steal it, right? Like, you have to acknowledge or either pay it or acknowledge it, in our case, for whatever you are reusing, right? um, so just like design, so if you here's an example of the design. Like, you have a system bus, system agent, which has a memory subsystem, L2 cache connected with a bus. Then you have another block which is a front end piece which has CPU fetch, decode, trace cache, and some branch prediction logic. So you put them into one block. And then you have out of order engine which has out of order execution logic, and retirement logic. And some of these blocks could be talking to each other, right? Like, and they can be connected on these interfaces. And then you have this integer and a floating point execution unit, which has cache and execution engines. So you put them into one function, right? And all of these functions can interact with each other, right? So, and so the way it's usually a art than a science. Like, how, what's the right partitions for the designs. Usually designers, architects, micro architects, they decide on the partitions. And uh, then another important piece is when partitions have been defined, you need some sort of clean interfaces so that different of these blocks can talk to each other, right? So um, once you have defined high level breakdown, then you can go deeper, right? Like, this is kind of a hierarchy for design. You start, lowest denomination is fub, or a design block. Above that there is a unit. So unit consists of multiple fubs. Fub means functional blocks. And then you put a lot of units together to form a cluster. And then you put a lot of clusters together to form your chip. And then you will put a lot of chips onto a system, right? So it's a pretty much hierarchical approach for the design. And verification will be same way, that you first verify at the fub level, then you verify at unit level, then you verify at cluster level and the chip level and the system level. So if we put this product development into a timeline, a linear fashion to simplify, um, and put them into different buckets, like, you start with customer requirements, like what do customers want in terms of features of a product, right? And based on that, you'll create the requirements spec by the architecture team. So these requirements could be performance, how what's the what are the instruction per second expected out of chip. What's the what are the key features you will be delivering me, what's the power targets, what will be the price range, budget, when it will be delivered, what will be the development cost, and so on, right? Like, so these are a part of planning phase based on understanding the customer needs. Then you go into the pre-silicon development phases, where you will start with high level design. Then that gets translated into logic design, and then that gets translated into physical design. um, and then you will do the place and route and send tape in your product, which goes to the manufacturing team. So they'll manufacture the chip, then perform the post-silicon validation, and once all of those functions have been done, you are ready to sell the parts to the customers, right? So this is a simplified version to show how the timeline looks like in a linear scale, right? Um, but in a actual product development, so if I describe just translating the same thing in focusing on the pre-silicon, you have architecture specs, RTL design, validation, then you will fix the bugs and do the schematics and give the products for the tape in. But what actually happens is something like this, where you define the architecture specs, you do the design based on it, you do the validation, and you find some bugs and issues. So those bugs can cause you to go back to fixing your architecture, fixing your design, and doing the validation again. And then you may find bugs again. And this kind of cycle just keeps going over and over and over again, right? Like what you will see that is that throughout the full development cycle, verification is done multiple times, and it's a continuous process, right? Like so, validation will start early in the project and then remains there till tape out or post tape out. These verification efforts will continue. In the project, like in you can look at the other functions like architecture starts and they get done somewhere in the middle of the project. Design team starts and they get done pretty much at the time of tape in. But verification, as I mentioned, they continue for longer period of time. And after the design changes have been done, like a lot of bug fixes can be done on the schematics, and the schematic teams they remain to work with verification engineers. So we talked about iterative loops and cycles, like um, usually for example, if you look at the Intel has been developing processors. Each next generation processor has more features, more better performance than previous one. Um, so usually these product development cycles become multi-generation cycles that you go through this loop, and then for next product you repeat the loop, and for next product you will repeat the loop. So, for example, in my own career, I talked earlier that I've been there in the industry for 28 years, and I've been seeing this loops multiple times. So now let's talk about additional data like verification languages for design and verification, ASIC languages, RTL languages. So languages wise, the top chart is for ASICs and bottom is for verification. So if you look at the design languages, um, VHDL has been there for decades and decades. It used to be the common verification language, but a lot of trend is downwards. Reason being is that there's a lot of legacy code which still sits in VHDL. So as I talked about reuse, a lot of new designs could be using some of these VHDL based designs, and the VHDL still is being used. A lot of new development is not done in VHDL, but there could be small incidences where people do development in VHDL. Verilog. Verilog has been a very popular language since late 90s, early 2000s. Um, the trend was big, but it is on a declining path. The reason being is that system Verilog has been gaining a lot of traction in recent years, right? So a lot of Verilog people who are rolling off from Verilog to system Verilog, and that system Verilog trend is continuing. In addition to that, there are high-level abstraction languages like System C. That's like a new language in development. So it's starting to gain popularity. It's in early stages. Similarly, C, C++, a lot of architects and all, they can write abstracted C, C++ code, which can be synthesized into RTL design. So there is increased work in C, C++, System C as well. But by default, like nowadays, most popular language is System Verilog for designers. When you look at verification languages wise, we have lots of languages. VHDL, Verilog, System Verilog. In addition to that, we have Vera, Specman, and other as well. So one trend you will see is that so Vera and Specman E, they introduce verification methodologies which were very good for including in our verification, which improved verification efficiency. some of those concepts have been combined into system Verilog and UVM because of UVM based methodologies, right? So because of that, like SpecMan, system Verilog is again becoming de facto standards for verification engineers. Also, the numbers are as high as like 70-80% of verification is done based in system Verilog, right? Next popular, which is gaining, is C, C++. So that's also gaining good traction. And in recent years, Python has also started to make its way into verification world. So for this class, we'll be focusing on UVM-based methodology around system Verilog, right? Talking about the methodologies, for verification again, like for base class libraries, UVM is gaining tremendous amount of traction, right? Like 80% of design projects are starting to use UVM, and that's what we'll be focusing in this class. Um, in addition to that, there are other methodologies, OVM, AVM. These were like precursors to UVM, and there's some reminiscence remaining because of the legacy IPs, verification IPs as well, Synopsys VMM, but majority of them you will see are on the decline in the interest of um, UVM. OVM was again precursor to UVM, which gained initial traction before UVM. A lot of people are migrating from these methodologies to UVM, right? And in this class, as I mentioned, we'll be covering UVM as a focus topic. Now, I'll talk about this important chart here. Like, once you become a verification engineer, where do verification engineers spend time? Again, based on the same research from Wilson, Mentor, and Siemens, um, what you'll find is that there are these functions: test planning, test bench development, writing the test, and running the simulations, debugging, and doing something else. What you'll find is that lot of verification engineers time goes into debug. Like 40% of their time is going into debug, and 24% is going into writing and running simulations, right? So you will do a lot of planning ahead, like 10% of your time, but you'll spend majority of your time writing test benches, running simulations, and debugging. Out of these, like test planning is one of the most important functions because that dictates everything else which happens after the planning. But we spend it requires less amount of time, so it's very efficient way to do the test planning and then spend time on other things. Over the years in verification world, from evolution point of view, there is always efforts to reduce these efforts on a given project, right? Like for example, right now you're spending about 60% of your time, 65% of your time writing tests and debugging. So methodology based approach, they try to make it more efficient for engineers to do these functions, right? So now let's look at um, basic test bench structure, which I think we'll cover it more in the next class as well. Um, but basic concept is that we have design under verification. Um, it is surrounded by some sort of stimulus generator, which is sending the test vectors into your design. And there is a driver which will be driving this stimulus into your um, DUT pins, and there'll be interface pins, which will be driven by this stimulation. um, and then results, they go into checkers and coverage monitors. So checkers will check whether responses from your design are correct, and coverage basically monitors that whatever uh, that whatever tests we are doing, are they able to cover majority of the design, right? So coverage is doing that. And finally, you have environment model, which is going to put all these test bench pieces, which could be initializing your designs, driving reset clocks, etc., for your design under test. So so there are three C's to remember: constraints, what type of stimulus you're driving, checkers, coverage. And the fourth C, which is being added, is collaboration, that design and verification teams have to work actively and cohesively. Um, And as I talked in the complex, as the design complexity is increasing, the size of these ASIC teams is increasing. It's becoming more important. Collaboration is very important function as well because of reuse. Communication is quite important for the engineers as well. And going back to our class project requirements, that's why we created slightly bigger sizes for the structure of the projects teams, um, so that they work in collaboration mode more often. All right, so I'll stop here, and I think we'll cover the remaining things in the next classes.